Welcome back to the Deep Dive, Curious Learners. Today we are strapping in for a high-velocity journey into the world of material science.
We really are. We're looking at this material that's been called a miracle material for years, graphene, and it just got this massive quantum upgrade.
Right, and we're talking about using, believe it or not, nothing but extremely fast pulses of light to completely revolutionize the fundamental properties of matter.
Yeah, it sounds like science fiction. I mean, it's the closest scientists have ever really come to performing alchemy. But instead of turning lead into gold, they're generating new, custom quantum properties on demand.
So it's about moving away from just using materials as we find them.
Exactly. We're moving from using materials as they are to dynamically designing them in real time.
And that's our mission today. A deep dive into the research that actually confirmed this is possible. It's the first direct experimental observation of something called Floquet effects in graphene.
And we're going to give you those aha moments. We'll explain why this specific way of controlling things using light is probably the key to unlocking the next generation of things like stable quantum computers.
This is your shortcut to understanding a concept that, for decades, was purely theoretical, but now it defines the absolute bleeding edge of physics.
It really does.
And just before we get down to the atoms, if you enjoy getting these kinds of knowledge shortcuts, please remember to like, subscribe, and maybe click on those affiliate marketing links for some recommended reading.
And you can also check out the Fourth Wall merchandise. We love seeing your suggestions for future deep dive topics in the comments, so keep them coming.
Okay, let's start with what we thought we knew.
Graphene.
Right. Graphene. It's been a fixture in science headlines for, over a decade now? When you hear that term miracle material, what are we actually talking about structurally?
Structurally, it's just perfection in two dimensions. It's a single atom-thin layer of carbon atoms.
Just one atom thick.
One atom thick, arranged in this perfect honeycomb pattern, like chicken wire. And the sources are really clear on why this structure is so amazing. It's incredibly strong, it's highly stable, and it's an exceptionally good conductor of electricity.
And we know what that stability and conductivity means in the real world, don't we? We've seen the potential for years.
Oh, absolutely. Think flexible screens that you can roll up, high-performance batteries that charge in a fraction of the time.
Or super sensitive detectors, advanced solar cells.
Exactly. Graphene is already a kind of high-performance athlete in the world of material science. But it always had this one fundamental limitation.
Which is that its properties were basically fixed.
They were fixed. Once you made a sheet of graphene, its conductivity, how it reacts to light, everything about it was essentially set in stone.
So if you wanted to change it, you had to use these sort of heavy-handed methods.
Precisely. In the past, if a researcher wanted to tweak the electronic states, they might use something called chemical doping, which is basically adding impurities.
Which sounds messy.
It is messy. Or they'd apply a physical voltage. And these methods are slow, they often create defects in that perfect structure, and they're generally static. You can't just flip a switch.
So the big question, the one this breakthrough really settles, was, can we cleanly and dynamically manipulate graphene's fundamental quantum properties after it's been made without even touching it?
And the answer is a resounding yes. The tool just isn't a chemical or a circuit.
It's light.
It's light. And that brings us to this excitingly complex name, Floquet engineering.
Right. When I hear engineering, I think blueprints, I think wrenches. When I hear Floquet, I think I might need a PhD. So what's the actual concept here?
Let's try an analogy. It makes it a lot simpler. Imagine a swing set.
Okay, a swing set.
If you just leave the swing alone, it has a natural way of moving, a fixed frequency, right? That's its static state.
Sure.
But what if you periodically kick or shake the support structure, the frame itself, at a very specific repeating rate? You can completely change how that swing behaves. You can make it go higher, maybe even vibrate in a new way.
And the light pulse is the periodic kick.
That's it exactly. Floquet engineering is the quantum mechanical version of that periodic shaking. It's an approach that uses these incredibly precise, ultra-fast laser pulses to hit the material over and over again.
And this rapid periodic driving is what reshapes the material's energy landscape.
Yes, what physicists call the effective Hamiltonian. It's fundamentally rewriting the rules for the electrons inside.
And that's a really crucial distinction, isn't it? We're not just, heating the material up. The high-frequency oscillation of the light is literally creating new rules for the electrons in the graphene.
But only for a moment. That's the powerful clean advantage. The electrons are forced into a new, temporary quantum state, a Floquet state, where they behave according to the light's rhythm, not the material's original structure.
So for a fraction of a second, they're turning a semi-metal into something brand new.
And then it just snaps back to normal, all with light. It gives them this precise, dynamic, and totally clean control.
It sounds less like a wrecking ball and more like a perfect dimmer switch.
A very, very fast dimmer switch. And this study, which was published in Nature Physics by the University of Göttingen and their collaborators, proved that this elegant optical control method actually works for materials like graphene.
Which was a big deal because people thought it might only work in insulators before.
Right. Proving it works in robust metallic and semi-metallic materials, that validation is the core breakthrough here.
Okay, that makes sense conceptually. You use light to kick the atoms. That changes how the electrons behave. But now we get to the really tricky part. How do you prove this temporary change actually happened?
Yeah, because we are talking about processes that happen in femtoseconds.
And a femtosecond is? What is that again?
The time scale is just... It's
Okay.
mind-boggling. A femtosecond is to 1 second, what 1 second is to about 32 million years.
Wow.
It's an unbelievably short amount of time. So you need a tool that can not only capture that speed, but also measure the specific quantum information that the light pulse changed.
And the tool for that was femtosecond momentum microscopy. Let's try and break that name down. Why momentum? Why is that the key?
That is the absolute key. The whole study hinges on it. When we talk about a material's electronic properties, how well it conducts, how it interacts with light, we're really talking about its band structure.
The band structure.
It's basically the map of all the allowed energy and momentum states for the electrons. Think of it like the approved highways the electrons can travel on.
So if the Floquet effect is real, the periodic light pulses should literally change the shape of that map. They should create new highways.
Precisely. And the only way to confirm that change is to look at the electron's momentum. And momentum microscopy does exactly that. It measures the momentum of electrons as they're kicked off the surface of the graphene.
Okay, so how does the femtosecond part come in? How do you take a picture of a change that vanishes almost instantly?
You use a clever technique called a pump probe. You need 2 separate light pulses, and they have to be timed with just unimaginable precision.
2
lasers. The first pulse is the pump. It's the intense high-frequency laser that actually creates the Floquet effect. That's the one doing the periodic kicking.
And the second pulse, the probe that takes the snapshot.
That's right. A second, much weaker pulse of light arrives a precise, controlled number of femtoseconds later. This probe pulse gently ejects electrons from the graphene surface.
And by measuring the momentum of those ejected electrons?
You capture a picture of that brief moment when the band structure was reshaped by the pump pulse.
It's just astonishing that we have technology that can coordinate those two events so precisely. And the data from this was the smoking gun.
It was. Dr. Marco Merbold, one of the researchers, said the measurements clearly prove that Floquet effects occur the photoemission spectrum of graphene. That technical phrase, seeing the changes in the photoemission spectrum, that's the undeniable proof. It showed that this light-based quantum control actually works in these critical systems.
So this moves us firmly out of the theory lab and into the engineering future. If we can now dynamically and cleanly control graphene with light, what are the big technological leaps this enables? What's the so what here?
Well, the immediate goal is the ability to custom design quantum materials on the fly. Professor Marcel Reusel, who led the work, he made it clear this opens up new ways of controlling electronic states in quantum materials with light.
So we're not just building devices from materials anymore. We're building devices where the material's own rules can be changed at the speed of light.
Exactly. And the most tantalizing application, the really big one, is the one that addresses the biggest bottleneck in quantum computing.
Instability.
Instability. This discovery allows for the investigation of creating and sustaining something called topological properties in graphene.
Okay, we have to spend a moment on that term, topological properties. It sounds intensely abstract. Why is topology so important here?
Let's try another analogy. Think about the shape of objects. Topology is a branch of math that's concerned with properties that stay the same even if you stretch or deform an object. The classic example is a coffee mug and a donut.
Right, and they both have one hole.
They both have one hole. So topologically, they're the same. You can imagine squishing and stretching the clay of a mug into the shape of a donut without tearing it. The hole remains.
Okay, so how does a donut relate to electrons in graphene?
In quantum materials, topological properties refer to these incredibly robust electronic states. They're often found on the surface or the edges of the material, and they are highly immune to defects, to impurities, or other local noise. They are, in a sense, topologically protected.
Like the hole in the donut.
Exactly. So if you could use Floquet engineering to imprint these properties onto graphene, you are essentially creating a material whose critical electronic pathways are inherently stable. They can't be easily broken.
Ah, and there's the quantum computing connection. I see it. The current quantum bits, or qubits, they're notoriously fragile. They suffer from decoherence, where the tiniest vibration can just collapse their quantum state.
It's a huge problem. But if we can use light to generate and control these stable, topologically protected states, which act like superhighways for electrons that defects can't interrupt, we're moving toward building reliable, robust quantum computers.
We're using light to write stability directly into the material's DNA.
Or its band structure, in this case. But yes, and that's the ultimate application. You're not solving the instability crisis with better shielding or colder temperatures, but with better light-engineered materials from the start. And this also applies to things like advanced sensors, letting them work reliably in noisy, real-world conditions.
It really is like creating an indelible ink using light pulses. The control is dynamic, but the state you create is robust enough to build the future on.
That's a great way to put it.
So let's bring all these threads together for our curious learners. We started this deep dive to understand the so-called quantum upgrade of graphene.
And we confirmed 3 core things. First, the miracle material graphene, known for being so stable and conductive, is now also confirmed to be subject to dynamic control.
Second, that control comes from Floquet engineering, using precise periodic light pulses to reshape the material's electronic properties, its band structure, on these ultra-fast timescales.
A cleaner, faster alternative to the old ways. And finally, this whole effect was validated using femtosecond momentum microscopy, a technique that lets scientists actually watch these fleeting quantum changes in real time.
And that opens the door to exploiting topological properties for hopefully truly stable quantum computers and next-generation sensors. It really is a new age for material science. And that brings us to our final provocative thought for you to mull over. If we have now validated our ability to design, control, and manipulate the core quantum properties of matter using nothing but light, and we can reshape those properties in mere femtoseconds, how fast will the overall pace of technological development accelerate when the very materials we build with can be redesigned at the speed of light?
The material bottlenecks are vanishing. The future is truly being measured in quadrillionths of a second now.
A profound thought to end on. Thank you for joining us on this deep dive into the quantum world of graphene and Floquet engineering. Keep exploring, keep questioning, and stay tuned for our next deep dive into the cutting edge of science.